Hi class, welcome to the next section, chapter 7.3. Today we're going to talk about the fundamental theorem of calculus and antiderivatives. Now that we have a basic idea of what an integral is, a definite integral, we can move forward towards the fundamental theorem of calculus. So this bridges the gap between calculus 1 and calculus 2. So the fundamental theorem of calculus part 1. Let f be a function that's continuous on a closed interval from a to b. Then we have a function g that we can define as the integral of f with respect to t from a to this variable x. Right? So let's think about what this is a little bit. So here we're taking a function. Notice that the function is not specified what variable is the independent variable. It's very possible that this function is a function of x and not t. Okay, actually that's typically what we use. So here we just replace the variable and call it t, and we go from a bounds of a to a bounds of x. Okay, x being somewhere within this interval of a to b. It could possibly be at b itself. Then what's going to happen is we are going to find this integral, and everywhere we see x, we actually replace with, everywhere we see t, actually replace with x. Okay, so here x is from a to b. Okay, so from a to this interval of b. So x is somewhere within this interval. G is also continuous on this interval as well, and it is differentiable on the open interval from a to b. Okay, so here the derivative of g is equal to this function f, right? So what this is saying is if I integrate a function, if I'm finding the area under a curve from a to anywhere on b, I can produce a function that will give me that area. That's basically what this is saying, okay? So the first part of FTC says that the derivative of an integral is the integrand function, right? So if I take g and I differentiate it, I will get f. So another way of saying this is that this is an antiderivative, basically, is where we're going to come to, right? So this is some function that if I took the derivative of this integral, right, once I actually calculate it as a function, I will get out the function that I integrated, right? So in other words, derivatives and integrals, they cancel each other out, sort of like functions and their inverse, right? If I start with a function and I take its inverse, I just end up with my input. So if I integrate a function, I get a new function out. And if I take the derivative of that new function, I start off with the function that I started with in the first place. Okay. So let's do an example. Here, let's find the derivative of the integral from 0 to x of t cubed minus 3t squared with respect to t. So this derivative basically cancels out this integral function, and what I'm left with is this integrand function, but with x as the input instead of t. Okay, so the integral and the derivative cancel each other out, and I'm just left with this exact same function, t cubed minus 3t squared, but instead of t, I have my function in x, right? So this is x cubed minus 3x squared. Here, this is a little bit different. I'm not going to x, I'm going from 0 to some function. So what we do here is pretty much the same thing, right? But notice that my formula is different, obviously, because I'm not going to x. So what I do is I use a u substitution. So I'm going to say u is equal to e to the x squared, and instead of taking the derivative with respect to x, I will take the derivative with respect to u. So then when the derivative and the integral cancel out, I will end up having to do the chain rule, right? Because I'm making a substitution. So I'm going to say let u equal e to the x squared. Then u prime, or the derivative with respect to u, is 2x e to the x squared. Using the chain rule, d over dx, the derivative with respect to x of this integral, will turn into d over du, 0 to u, and the same function. Okay, And then, using the chain rule, I will also have the derivative of u with respect to x. Okay, so I take the derivative with respect to u. Since u is a function of x, I also have to take the derivative of u with respect to x, right? So, chain rule. Substituting all of these terms in, this d du and this integral function just cancel out. So I will have u cubed minus 3u squared, so I'm using u's right now. And then I will have my derivative function of u with respect to x, which is this 2x e to the x squared, right? So times u prime. Make my substitutions for u. So u will be substituted and my u prime substituted as well. So here I'll have e to the x squared cubed minus 3 times e to the x squared squared, and then my u prime will be 2x e to the x squared. So from here I just need to simplify, so I'm going to cube this term and square this term. So here I have this times itself 3 times, so there's 3 of these, right? So e3 x squared minus 3e 2x squared. And then multiply times the 2xe x squared. I'll just multiply through this e to the x squared, so that'll bump all of these up by 1 more, right? They'll just add 1 more to each one. So there's 4, and this turns to a 3. I'm going to keep this 2x on the outside. I could have just pulled out the common e to the x squares here and added it to this term that I have outside, but for me it's easier just to see how many total I can pull out. So total I can pull out 3, right? That's the GCF for these e to the x squares. So my final answer is 2x e to the 3x squared with an e to the x squared minus 3 on the inside. So again, I could have gone straight there from here if I just pulled out 2 from each side and added it to this term, but for me it's easier just to kind of condense each type of function that we have here in these terms so that I can get to the final answer. So that's just a personal preference, but that's the way that these works, right? So I gave 2 examples, one that's very, very straightforward. This is the kind of problem you're going to see most often when you see these. However, of course, it's good to know how to deal with something that's a little out of the ordinary. So when you see a function here, instead of just regular x, you want to make a u substitution and then use the chain rule, right? So here everything will be in terms of u, and here this is one of the times where that Leibniz notation is preferable to the Newton notation, and it makes it a lot easier to understand what's happening by looking at, oh, I'm just differentiating this term, right? This d du, it's this whole integral function on the inside that is being differentiated with respect to u. Chain rule says u is a function of x, so I also have to differentiate u with respect to x. So this inside function here, this integral, is being differentiated with respect to u, which is why I got it in the form that looks like this. Some lower bound to my variable. In this case, instead of x, I'm using u because of my change of variable here. And then, like we said before, implicitly using the chain rule, I have to differentiate u as well since it's a function of x. And then I can just substitute all my stuff in, and then simplify. So that's what we did here. So that brings us to antiderivatives. Okay, so here we haven't used an antiderivative yet. We just understand from FTC part 1, right, the fundamental theorem of calculus, that derivatives and integrals undo each other, right? That's the mathematical relationship, which is kind of strange if you think about it, because derivatives are rate of change and integrals are area under the curve. So there is a relationship there, right, between instantaneous rate of change and the area under a curve. So mathematically speaking, right, as far as like the calculus that we're trying to do, it's very important to understand that these things undo each other, right? So if I differentiate something, I can come back to my original function by taking the integral of that function. Or if I integrate something, I can come back to the function I had originally inside the integral by differentiating. So it's a way for us to go back and forth, back and forth. Again, kind of like a function and its inverse. It allows us to go back and forth from the domain and range, right? So antiderivatives. An antiderivative is a function, okay? It exists on an interval I if the derivative of this antiderivative is equal to a function f for every x on this interval, right? Meaning that this is again coming straight from the FDC part 1. It's saying that an antiderivative is any function such that if I take its derivative, it will give me a function f. Now, when we do this in terms of an integral, we're thinking about functions that if I were to integrate this function, it would give me the function that I had originally inside of my function. So it's really just a result of the FTC. Okay. So again, an antiderivative is kind of the way to undo a derivative. It's the opposite of a derivative, if you will. Right? So for instance, I know that the derivative of x squared is 2x. That means the antiderivative of 2x is x squared. Right? So if this is the function I start with, its derivative is 2x. If I were to start with 2x, okay, if I start with 2x, then the antiderivative of 2x is x squared, right? So it's the way that I go back. It's what function would I need so that if I took its derivative, I would get out the function that I have. So it's going in the opposite direction. So again, notice that when we have the lowercase for a function, that's our function. The uppercase is generally reserved for the antiderivative function. Okay. So when we do antiderivatives, there's actually families of functions, meaning that, for instance, the function 2x has more antiderivatives than just x squared. In fact, there's an infinite number of antiderivatives for the function 2x. There's an infinite amount of functions such that if I were to differentiate them, I would get 2x. So for instance, consider x squared plus 1. If I take the derivative of x squared plus 1, I get 2x. If I take the derivative of x squared plus 5, I get 2x. If I take the derivative of x squared minus 7 pi, I get 2x. So for 2x, there's an infinite number of functions which if I were to take their derivative, I would get out 2x. So there's an infinite number of antiderivatives. So this doesn't work for differentiation, but it works for antiderivatives. Okay. So they're a complete family of functions. So g of x has an infinite number of options. So again, the derivative of g prime, the derivative of capital G should give me the function I'm interested in. That's how I understand what an antiderivative is. So any function such that it's x squared plus c, where c is a constant, will get me 2x, right? So there's an infinite number of antiderivatives for 2x. Any constant value I choose here will work, right? C has to be a real number. So since differentiating the constant term makes it disappear, I have an infinite number of options. So if f is an antiderivative of a function, little f, on an interval, then the most general antiderivative of f on I is big F plus c, right? So this is the most general form for an antiderivative, right? So this is just a theorem stating what we showed here from this previous definition. C being in R. All right, so now we're going to look over a list of some common antiderivatives. Now this might be a little bit difficult at first because for about half of the semester, we've been really focused on differentiating a function. So now what we're going to do is we're going to have to talk about anti-differentiating. So we're going to start with a function and we have to now think in the opposite direction. What function do I need such that if I were to differentiate it, I would get the function that I want, right? So we're going to start with f of x and think, okay, now if I what function do I need to differentiate in order to get this function out, right? So we got to think in the opposite order. So first we're going to start off with just some general rules and general properties, right? So if we have a constant times our function, then for the antiderivative, it's just going to be a constant times the antiderivative. That should make sense because remember what an antiderivative is. It's basically an integral, right? And what is an integral? An integral is a limit and a sum, right? And we know that for limits and sums, we can always just pull out that constant multiple. So it makes sense that the antiderivative of a constant of a function is just the constant times that antiderivative. Okay. Here, if I have two functions being added together, again, just think about what are the properties of limits and sums. If I have one function that is I can look at as a sum of functions, well, then I should be able to look at it as the sum of antiderivative functions, right? So little f plus little g, its antiderivative should be the antiderivative of f plus the antiderivative of g. Now again, I don't have the plus and minus form here, but minus is included because remember, subtraction is really just addition, right? If I want to subtract numbers, I'm really just adding a negative value of another number, right? So 2 minus 3 is just 2 plus negative 3. So whenever you see me write just a plus, this also includes negative, okay? Let's think about the function x to the n, the power function. Now this is a very important function. Now when we talked about derivatives, when we first started formulating actual generalized rules for finding derivatives, the power function was the very first function that we started with. I want you to take a second and think about what you think the antiderivative of a power function would be, okay? Now, again, what would the generalized form be of something where when I take its derivative, I end up with x to the n? So again, we're thinking backwards. So what would be the generalized form of something so that when I differentiate it, I end up with x to the n? So I'll give you guys a second to think about your own. Maybe you want to pause this and work on it and come back and see if you guessed right. I'll do this for the entire list, by the way. So the function that we would need is 1 over n plus 1 times x to the n plus 1. Now think about this. Maybe you need to pause this video in just a second. Take this function and take its derivative. Okay, take the derivative of 1 over n plus 1, x to the n plus 1, and you should come up with x to the n. So you can go ahead and pause it now if you wish. Okay, so hopefully you paused it for a second and you differentiated this function and you saw that we come out with the exact same thing, right? So if you think about differentiating this, you go n plus 1, it drops down to a multiplier. So the n plus 1 over n plus 1 cancels to 1, they cancel with each other. And the degree of n plus 1 drops down by 1, which will give you n. So it should make sense that if you differentiate this, you end up with this, which means that this function is the antiderivative of this, right? So if we start here, okay, the antiderivative of this function will be this. So the way that we find this is we increase this power by 1 and we multiply by the reciprocal of that new power for the antiderivative. The reason that this doesn't work with -1 is because -1 gives me 1 over x. Now, can you think of what function it is that we have such that if we differentiate that function, we get 1 over x? So again, you can pause it, take a second, and think about it. What function do we have that when we differentiate it, this is what we get? That's our antiderivative here. So the antiderivative of 1 over x, so the function that we would differentiate and end up with 1 over x, is natural log of x. This is why we reserve -1. So x to the -1 is 1 over x. So we cannot think of this as a power function like we normally would. Normally if we had x to the -1, we would just differentiate it. But for antiderivatives, it does not work that way. So we cannot use 1 over x. Okay, and think that we'll be doing a power function, I should say. E to the x, this is an easy one, right? So if you think about e to the x, whenever we differentiate e to the x, we get e to the x. So the antiderivative of e to the x is e to the x. Okay. What about b to the x, a logarithmic function, right? So here's a little bit different because it's a little difficult to think about what the derivative of a power function is, or I'm sorry, an exponential function is, but the antiderivative will be a little bit more difficult, right? So here, it's 1 over natural log of b times b to the x. So normally, we had natural log of the base times b to the x. Here, it's a little bit different. It's 1 over the natural log of the base times b to the x. Okay, so I wouldn't expect you guys to get this one, but it's nice to have it available when we need to find antiderivatives of these things. Cosine x, so just think about what we have for the trig functions. So what do I need to differentiate in order to end up with cosine? Well, we know that it goes cosine sine, cosine sine, cosine sine. Well, what about the sines, right? So what would I need to differentiate so that I end up with a positive cosine? I know it'll be a sine function, but is it a positive sine or a negative sine? Take a second to think about that. Okay, hopefully maybe you paused it and you went over it. Maybe you wrote down the cosine sine, cosine sine, cosine sine for the derivatives and you changed the signs appropriately. And then you just kind of move backwards a step when you have cosine, and it should be your regular sine. Now, if you wrote down the cosine sine, cosine sine, cosine sine, then you should also be able to go and say, well, for sine, I know I need to have negative cosine, right? So think about that. If I differentiate sine, I get cosine. If I differentiate negative cosine, the sign changes and I get sine. So here it's really important to understand that for antiderivatives, it actually works the opposite way. Normally, when we take the derivative of cosine, we know it goes to sine and it changes sign. However, for the antiderivative, it does not change sign because you're doing the opposite of what you would for the derivative, so it stays the same. For sine, normally it would go to cosine and the signs would stay the same when we do a derivative. But since we're doing the antiderivative, it does not stay the same. It actually changes sign. So I get a cosine, but it changes sign to be negative. So you have to understand that if you use that sort of verbiage that I use every time we did cosines and sines for their derivative, we have to do the opposite of that, right? So cosine does not change signs for the antiderivative, and sine does change signs for the antiderivative. Okay. Here's secant squared, so think about your trig functions. What function would I need to differentiate in order to get secant squared? That's my antiderivative. So hopefully you're familiar with this, and you say, oh, I know that one. The derivative of tangent is secant squared. So that means that tangent is the antiderivative of secant squared. If I start with secant squared and I say, hey, what is its antiderivative? It's tangent. Okay. Secant times tangent is secant, and 1 over square root 1 minus x squared. That is one of our inverse trig functions, sine inverse. So if you notice, really what's going on here is we're just starting with functions here, and their derivative is what we're looking at, right? So if you want to be able to look at a function and its antiderivative, you can go to that list of derivatives that I have, and you're just kind of going backwards, just like you would for an inverse function, right? So here 1 over x squared, if you remember what this is, this should be your tangent function, right? So tan inverse, cosh, right? So what do I differentiate to get cosh? Well, it should be sinh, okay? For sinh, what did I have to differentiate in order to get sinh? It was cosh, right? And so that's all the ones that I'm giving you here. But again, you can go to, in this course reader that I have, I think it's section 4.9, and give you a list of derivatives. It's like 36, 39 derivatives or something like that. You can use that list to figure out what all the antiderivatives you're going to use is going to be. But these are the most commonly used ones. Specifically, the one for polynomials is the one you're really going to see the most, right? Sine and cosine is going to pop up. These other ones, you may run across them in your homework or something like that, but they're not super important right now. Because as we get towards calculus, like really into calculus 2 stuff, the focus doesn't necessarily become the antiderivatives, but it's methods of finding these antiderivatives. Just like for differentiating, we had very complex derivatives that we had to calculate, and there is methods for finding the derivative. That's the focus of calculus 2. It's not just, oh, the antiderivative of this is this function. It's more so like there's several methods and approaches to finding out exactly what we have based on the form of the function, okay, of the function that we're given, because again what's going to happen is we're going to have combinations of these functions being multiplied, being divided, functions inside of functions, just like we did for derivatives. Okay. So this brings us to the fundamental theorem of calculus part 2. Now don't worry, there's only two parts. There's part 1 and part 2. Part 1 is very important, so is part 2. Part 1 tells us that derivatives and integrals undo each other. That's this idea of a derivative and its antiderivative. Okay, so this is how we're going to find the values of derivatives exactly, which brings us to the fundamental theorem of calculus part 2, the FTC. The FTC part 2 tells us how to find the value of a definite integral exactly using those antiderivatives. Okay, so let's say that we have a function f, little function f, that is continuous on a closed interval from a to b. So again, a and b is included. Then the integral from a to b of that function that we look at is equal to the antiderivative of that function evaluated at the bounds. Okay, so in the antiderivative, I'm going to plug in b, and I'm going to subtract from that my lower bound, a. Now you might say, well, hey, that's not too bad. It's not terrible, but it can be extremely difficult. So I will throw this out there right now. Calculus 2 is definitely much harder than Calculus 1, not to throw you guys off or to scare you at all. But I think that this class so far will prepare you very well for Calculus 2. So at some point I will develop a video series for all the Calculus 2 and the Calculus 3 material. So this should be a good precursor to that course, right? So again here, f is any antiderivative of f. So that is that f prime, if I were to take the derivative of this big F function, I would end up with the little f that's inside of my integral, my integrand function, right? So again, just to summarize, that part 2 of the FTC says that we can evaluate an integral by looking at the antiderivative. Okay, so we will introduce a little bit of new notation here as we go through these examples. But again, these are the most basic examples. They're very straightforward. There's no like crazy tricks popping up yet. Those are the things that we'll see as we go through Calc 2 material. Okay, so let's find the integral from 0 to 1 of x cubed minus 3x squared dx. So if you notice, this is the same function from the beginning, but the difference is that here we used FTC 1, right? The first part of the fundamental theorem of calculus. So we didn't actually calculate this integral. We used FTC to differentiate the integral and said, hey, by the way, they cancel each other out, and now you get your new function in terms of x, what that upper bound variable was, right? So now we're going to actually calculate this integral over an interval from 0 to 1, right? So we're going to bound it from 0 to 1. We want to know what is the area under this cubic function, right? So the area under this cubic function from 0 to 1, if there's any points that are negative or below the x-axis, it takes away from that area from 0, between those bounds of 0 to 1. So again, recall that we found this in the last lecture. Actually, we used this in the last lecture, in the last video. I forgot as well, using the limit sum definition of an integral, and we got the value negative 3, 4. So we use this, and we use the midpoint rule. We use the left-hand sum, the right-hand sum, and we used the limit sum definition to find the exact value, and then we compared the errors, right? So we did this what I would call the long way, right? So now using antiderivatives, we can use this in a shorter form. So we're going to use 3 different properties here, right? So the easiest way to do these, well, we don't always have to do this using these 3 properties, but the first property we're going to use is that we are going to separate this into 2 different functions, 2 different integrals to find the antiderivative. And then we're going to pull out the constant value in the second form, the second integral that we have, and then we're going to use this power form. So if you need to write this on your lecture notes on the side real quick, go ahead, because we're going to use these all 3 of these formulas like right now. So maybe you want to pause it and write that down on a piece of side of your note paper. Then let's go over this together. So let's go ahead and pause this and let's have you attempt this first. Okay, so I'll be quiet for a second so you can pause it, and then we'll come back and then we'll check our work together. Okay, hopefully you took that time to attempt this problem. And now let's go ahead and check our work together. So we're going to take this and let's use that property of integrals and split this across, because remember, an integral is a limit and a sum. So any properties that limits and sums have, we can use for integrals, which is one of them being, if I have a function that I can consider as two functions being added or subtracted, I can separate them to two different limits or two different sums, or in this case, two different limit sums, which would be two different integrals. Okay. Remember that when we're using integrals, this little dx here is very important. I will take off points if you do not use the proper notation as you go through these problems, for those of you who are in my class. Okay. So when you're doing integration, you always include the bounds for integration and the differential that you're using. Okay. Because if I were to write dy here, this would become a completely different problem, even if all of my variables were x, but my differential was respect to y. So it's very important that you keep that differential so that you let the reader know what variable it is that you're integrating with respect to. Okay. So using the fundamental theorem of calculus, I'm going to take this, and I generally would split this in half. I can go right at it as I want, but I'm going to look at it in pieces. So the antiderivative of x cubed is 3 turns into 4, and we multiply by the reciprocal of that new power, right? So it's 4 and 1 over 4. This negative 3, okay, this 3x squared, 2 goes to 3, and I multiply by 1/3. I then have to evaluate this at x equals 0 and x equals 1, okay? So this line here means that I plug in 1 everywhere I see x, and I subtract from that me plugging in 0 everywhere I see x. So this line here means I evaluate at 1 and subtract from that, be evaluating at 0. So here all I did was simplify. This 1/3 and this 3 cancels out, so I'm not doing extra math that I don't need to. If I plug in 1 everywhere, I get 1/4 minus 1. And I will subtract from that me plugging in 0 everywhere, which is just minus 0. So this turns into 1/4 minus 1, or negative 3/4, right? So this is me plugging in the 1, this is me plugging in the 0, which turns into 1/4 minus 1, okay? Because 1 cubed is 1. This whole thing goes away to 0. So 1/4 minus 4 over 4 is negative 3/4, which is exactly what we got from the very end of the 7.2 lecture video. Okay, so that's our first integral that we've evaluated. Hopefully you got the same answer. Now let's do the next one. Okay, let's integrate sine of theta with respect to theta. You see why the differential here is very important. It's telling me that I'm integrating theta. And let's do that from 0 to pi. So go ahead and pause this and do this on your own. Think of the antiderivative, evaluate it at the bounds, right? So you're going to plug in pi and you'll plug in 0 and you'll subtract the two values, and then you'll get your answer, right? So let's take a second and then we'll come back and compare work. Okay, hopefully you paused the video and went ahead and worked this on your own. So I need to find the antiderivative of sine, which I gave you a list for. We should definitely start learning how to memorize these or understanding what the antiderivatives are. So normally we know sine always goes to cosine and cosine goes to sine, but we got to figure out about the sign change. When we differentiate sine, the sign stays the same. So when we do an antiderivative, it does change signs. So the antiderivative of sine is negative cosine. Okay, so to evaluate this, I will get negative cosine, and I will evaluate that from pi to 0. Okay, which means that I plug in pi, and I also plug in 0, and I subtract the two values. So I will get negative cosine pi, and I will subtract from that negative cosine of 0. So cosine of pi we know is negative 1, cosine of 0 we know is 1. So that gives me negative 1 minus a minus 1, or 1 plus 1, which is 2. Okay. So coming to part C here, we want to find the integral from 1 to 4 of 3x squared plus 1 over 2x. So I want you guys to go ahead and try this one yourself as well, especially since we've gotten 2 under our belt already. All right, so go ahead and pause this and work your own math, and then let's compare our answers. Okay, hopefully you paused the video and you came back, and let's go ahead and do this. So we don't have any examples yet where we have a function over a function. In fact, these can be extremely difficult where we have one function over another. As you remember, when we do derivatives, we'd have to, if we were to take the derivative of this, we'd have to do the product rule. So when you think of doing the antiderivative, you're probably thinking of some sort of anti-product rule, which there actually is none. Sorry to burst your bubble. Generally, when we come to these, there's several approaches that we would try, but we're not there yet, right? So really what we want to do is just think about when we're taking derivatives. And I gave you problems like this in the power rule section, which is simplify first, okay? You can always simplify things. You don't have to just brute force it and say, let me figure out how to do this as it is. Generally, you want to try to simplify things. So in order to simplify this, we have a numerator that is a polynomial and a single monomial in the denominator. So we can distribute this to both terms and simplify, right? So first we're going to simplify the integrand. So this gives me 3x squared over 2x plus the integral of 1 over 2x, or we can keep it all inside of one integral. It doesn't really matter, okay? But the nice thing is, now it's a lot simpler to deal with. We have a 1 over x, which we have an antiderivative for, and we have a 3/2 x, which we also have an antiderivative for, because this is a power rule. This is not a power rule, okay? So we can separate this into two different functions. As you noticed up here, I was talking about doing that for part A, but I never did. I just took my two forms, my single function, and I just started to apply my rules, right, of antiderivatives. That's always fine. You can do that. Or you can take this and you can separate it into separate integrals, right? So notice I have the dx at the end of both, because that completes the integral function. So I have the integral from 1 to 4 of this first half and from 1 to 4 of this other half. Typically when I see a constant multiple, I like to pull that out, okay? So before I get into the nitty gritty, I always pull out the constants because it throws me off. I like to just focus what's going on inside the integral. So this is really just a function of x, and then whatever I do here, I'll end up multiplying by 3/2. So if we focus on the first one, this is a power function with an exponent of 1. So remember the way that this works, we increase the power by 1, so this will turn into x squared. And for that new higher power, we multiply our function by its reciprocal. So this will turn into 1/2 x squared, and I will multiply it by 3/2. Okay. Here, remember we have a special rule for when we have a power function with -1 as the exponent. Here the antiderivative is natural log. So here the antiderivative is going to be the natural log function. So I'm going to take this 3/2 times 1/2 x squared, which is the antiderivative here. This 3/2 just came along for the ride. And I'm going to evaluate this from 1 to 4. Notice here I didn't put the variable of the bounds, right? Here I said theta is pi, theta is 0. In the one previous I said x is 1, x is 0, because that was the variable we're using. It doesn't really matter if you use that notation or not. As you get higher up in your math courses, you'll notice that most people do not include the variable and say what it is equal to. It's assumed already that the variable here is x, and that's what we're going to have. Now, when you get to calculus 3 and you have multivariable functions where you see x's and y's in here, which is why it's important that you signify to the reader that you're integrating with respect to x or to y or to z or to theta or to r or to whatever function it is. It's because if I have multivariables here, multiple variables, then yeah, it's very important that I say well, I have x's and y's in this thing, and x is what I'm evaluating from 4 to 1. So x equals 4 and x equals 1. That would be very, very, very important in that case. So when we're doing just a single variable like we're doing here, and for most of calculus 2, you don't really have to include the variable name here. Okay, so here you'll see me start to slowly integrate ourselves into the standard notation that we use when we don't need to be very, very specific, right? So here I'm just putting 4 to 1. This is the only variable present, so it's assumed that that's the variable that I'm evaluating from 4 to 1. Here I'm going to add to that this integral, right? So the antiderivative is natural log, and I'm going to evaluate that from 4 to 1 as well. I don't have to put x because x is the only variable present. So here I can simplify this to 3/4 x squared. I'm going to plug in 4 to this, and I will subtract from that me plugging in 1 to this, and I will add to that natural log evaluated at 4 and subtract from that natural log evaluated at 1. Okay, so here I have 3/4, plug in 4, subtract from that 3/4, plug in 1. I will add to that natural log of 4 minus natural log of 1. Now it's nice because natural log of 1 is 0, and then I can simplify this stuff, and then this is just natural log of 4. I don't have to put it in decimal form. I'll just keep everything exact. As you know, in this course, that's how I prefer things. So here we'll have 12 minus 3/4 plus natural log of 4. I'll combine these two numbers, this fraction here, and I will have my final answer. Okay, so next let's find the integral from 0 to 2 of the absolute value of 2x minus 1 of dx. Now this one is a little bit tricky. Maybe you want to try this on your own. Maybe you want to just wait for us. That's fine. I'll give you guys a second where I don't say anything so you can pause it if you want. Okay, so maybe you try this on your own. Maybe not. That's fine. Here, the tricky part about absolute value of 2x minus 1, if you notice through our list of antiderivatives, there is no antiderivative here. Okay. We also never, at least I don't think we have, talked about how to differentiate an absolute value function. It is possible, but we didn't really cover it. It's not the most important thing. It's not something you see all the time, right? Like it's not something I run into throughout my mathematics journey as I'm doing stuff. So we'll talk about that now, especially for this antiderivative, right? This integral. In order to differentiate or to integrate an absolute value sign, you have to break this down into its piecewise equivalent, meaning that an absolute value function is really multiple functions at once, okay? Because we have a negative case and we have a positive case. So this 2x minus 1 can be broken down into two separate functions, and we can use our properties of integrals, which we showed in the last section, 7.2, that we can break things down into smaller integrals over one continuous interval, right? And that's what we would do here. So 2x minus 1 equals 0 at the point x equals 1/2, which means that I can break this down into two integrals where I go from 0 to 1/2 and from 1/2 to 2. 2x minus 1 is a line, so its absolute value is actually two different lines. So to visualize this, we are in Desmos. This is the function that we're interested in, but notice that we are only interested in it from 0 to 2. Okay, so I want to find the area under this curve. So from here, notice that it's two different functions. It's continuous, but it's two different functions. So I want to break it down to an integral from 0 to this point, and then from this point to 2, right? So we can say that this is what I'm trying to find. The area above the x-axis, but below this curve. That is what we are calculating right now. So if you notice, we could do this another way by looking at triangles, right? I can say, well, I have the height of a triangle and I have the base, so I can find the area. I have another triangle where I know the base and I know the height, so I can find its area. Now, this is really only useful if I have a visual representation of this, right? So sometimes it might be useful for us to stop and plot a graph especially if we have a line. But generally when we have a curve, right, like x squared, that's not going to be super helpful. That's why we use those rectangles to approximate, but now we have a method of finding absolute, the exact value. So, oops, there we go, 2x minus 1. So this is what we're trying to find, okay? And actually we can verify our answer by calculating the area of these two triangles and adding them together. Okay, so first things first, I found where my function was 0 so that I know where to split this up into its two parts, right? So absolute values don't have an antiderivative, so we divide it into two different integrals, right? So the integral from 0 to 2 of the absolute value of 2x minus 2 is the same as the integral from 0 to 1/2 of the negative version of this, the line that's going downwards, okay? 2x minus 1 being negative, and the positive form of this from 1/2 to 2, because 2x minus 1 is a positive line. So we have the negative form and the positive form. Okay, that's why I have a negative on the outside. If we wanted to, so again, this negative is applying to both of these terms. It is not just saying negative of 2x. It's a negative 2x and a positive 1 because this negative gets distributed. But a negative sign is a constant, so I'm pulling it out. Okay, I could keep it here and say it's the integral of negative 2x plus 1, but it's not necessary. Let's just find this integral, and then we'll change the sign at the end, right? So here I have two different integrals, two different bounds, the same integrand function, except for one is negative and then the other is the positive form, because absolute values give me two different lines, right? So the antiderivative of 2x squared, the 2 also can get pulled out if I pull these into two different functions. This power of 1 goes to 2, and then I multiply by the reciprocal of 2. So that's why I have the 1/2 x squared. This 2 is this 2. Okay. The antiderivative of 1 is x, right? I know that if I differentiate the function x, I always get just the constant value 1. Okay, so the antiderivative of 1 is x. Here I get the same thing, this 1/2 x squared from this 2x, and this one also goes to x, but I'm evaluating at different bounds. Notice I keep my parentheses here, and this negative is in front. Okay, the bounds that I evaluate are from 1/2 to 0, 1/2 and 0 I should say, and the bounds here are 2 and 1/2. So I'll plug in 1/2, and I will plug in 0 and subtract these. I will plug in 2 and subtract from that me plugging in 1/2. Okay, so I have this 1/2 squared minus 1/2 minus 0 minus 0. So first I'm plugging in this 1/2 here, right? So this goes away. So 1/2 squared minus 1/2, 1/2 squared minus 1/2. Subtract from that 0 minus 0. And you see here I keep this negative out front. So that will distribute to each piece. The 0 minus 0 goes away, so we don't have to worry about that here. I think my notation's off a little bit. I think I should be closing this parentheses as well, because this should be, if you think about it, it would be a plus, right? So negative and a plus, but it's fine because the zeros go away, so it doesn't matter about this bad notation. Here, it's pretty straightforward. It's this 2 squared minus 2, and I'll subtract from that this 1/2 being squared minus 1/2. Notice I have my parentheses here. It's very, very easy to get lost in all the pluses and minuses, especially if I'm already subtracting something, and then when I evaluate these bounds, I'm subtracting on top of that. So make sure your parentheses are clear for you. As you see, I've already made a mistake for myself, which I've actually already fixed like 3 times. So just make sure you keep track of your negative signs and do everything correctly, right? So here, I'm going to have a 1/2 squared minus 1/2 being subtracted. Okay, and that's the same thing that I have here. So I actually have 2 of these things, so I can combine those. This 0 goes away, and this turns into 4 squared minus 2. Okay, so I have a 1 squared minus 2. I have 2 of those because there's a negative 1 from this. Remember, the zeros go away, so that doesn't matter. So I have a 1/2 squared minus 1/2, 1/2 squared minus 1/2. They both have a negative in front, so there's actually 2 of those, negative 2 of those. Then this is just this 2 squared minus 2. So this turns into 4 minus 2, or 2, right? This turns into 1/4. when I distribute this, I get a negative 1/2. And then when I distribute this negative here, I get a positive 1. So here, 1/4 times the negative 2 is the negative 1/2. This times negative 2 is a positive 1. This is my 4 squared, right? My 2 squared is 4 minus 2. So when I combine all of these, I get 5 minus 2, which is 3. 3 minus 1/2 is 2.5, or 5/2. Okay. A picture of the graph. So we saw this earlier on Desmos. So we know that this small one, this halfway point right here, it's exactly at 1/2 because we know this is 2 different lines. So a height of 1 and a length of 1/2, right? So the area of this is 1 times 1/2 times half. So this is 1/4. Okay. Here we have 1.5 times 3, which is 4.5. And then if we divide that in half as well, and add these together, we'll get 5/2 as well, right? So you can go ahead and do that by hand if you want to just verify it geometrically that we have this correct area. Okay. So this brings us to the net change theorem, which is really just talking about how much have we changed from one point to another. We've seen this before a little bit, but not in terms of an integral. So the integral of a rate of change function gives us the total change of the function. So remember, an integral gives us the area under a curve, right? How far we've traveled if we've had a velocity function. So if we have a function that tells us the rate of change, the integral will tell us the total change, right? So the integral of f prime, the derivative function, is that original function, the antiderivative, right, evaluated from b to a. So let's do a quick example. If v of t is the volume of water in a reservoir at time t, then its derivative, its rate of change at which the water is flowing into the reservoir, is v prime of t, right? So v is the volume of water. The rate at which the volume is changing is v prime, okay? So if we're interested in the change in volume from time 1 to time 2, right? Let's say from 5 minutes to 12 minutes, we would integrate the derivative function, which tells us the rate of change, over that time, and it'll tell us how much we've changed. And so the antiderivative of the derivative is its original volume function. Okay. This brings us to indefinite integrals. So here we're just giving you an example of an application of how this works. An indefinite integral is similar to a definite integral, except that an indefinite integral is not bounded, right? So when we find an indefinite integral, when we evaluate one of those, we have to give a generalized antiderivative function. So an indefinite integral will give us out a function. A definite integral is bounded and we get out a value. Okay. Oops, skip that. So an indefinite integral is an integral that is not bounded. A definite integral will give us a value. An indefinite integral will give us a function. It's very important to understand the difference between these. So if we don't have bounds on our integral, it's an indefinite integral, and the output that we get from that is a function. So let's look at some of those common indefinite integrals. This is pretty much the same as the one that we had for antiderivatives. Okay, so if we have a constant times a function, then I can pull that constant out and have it as a constant multiple of my integral. And my end result then is the constant times the antiderivative function plus any constant value. Okay. Here, if I have an integral that I can consider as the addition or subtraction of two functions, I can separate that into two separate functions, and then I can evaluate that as the sum or the difference of my two antiderivatives plus a constant value. Okay. Here, if I have the integral of just a constant value, then that will bump up to a value of x plus that constant value. Okay. For a power function, it is the antiderivative of the power function plus a constant value. Again, here we have a restriction on the power. It cannot be -1 because that is restricted for the natural log function, right? So the indefinite integral for 1 over x is its antiderivative of natural log of x plus any constant value. Okay. Here we have e to the x is e to the x plus c. B of x is its antiderivative plus any constant value. So really what's happening is if it's not bounded, it's the generalized form of the antiderivative. It's any family of functions, an infinite set. C can be any number, pi, -3, square root 2, it can be anything, right? So we just write that as C. Sine of x is its antiderivative plus C. Cosine is its antiderivative plus any constant. Secant squared is tangent plus any constant. The indefinite integral of cosecant squared is negative cotangent plus any constant. So again, just notice that this list is really just coming from our list of derivatives, right? Here we have sine inverse, tan inverse, etc. I'm not going to go and do all 39, 40, 36, however many derivatives that we had, but you should get the idea and be able to find your antiderivatives for the general functions that we have, right? Cautious cinch, and so forth and so forth. So let's go ahead and do an example where we are not evaluating at bounds, right? So an indefinite integral is actually much easier to evaluate than a definite integral because you just need the antiderivative. You don't have to evaluate at bounds and do all of the subtractions and things that we're doing before. Just don't forget to include your constant of integration, right, which is that c value. So here we want to find the indefinite integral of 8 over square root of x. It is not bounded, so we will get out a function, and we will add the constant of integration, c, at the end of that function. So here as it stands, this is kind of difficult, so let's put it into a form that's easier to deal with, which is to rewrite x as a power function, and let's pull this 8 out as a constant of integration, right? So I can rewrite this with 8 on the outside, and instead of square root of x as a denominator, I can have it as x to the -1/2. And I just do all my rules. Remember, derivatives go down by 1. Integration goes up by 1. You're going in the opposite, right? So instead of this turning into -1/2 times x to the -3/2, which is what happens when we differentiate, we do the opposite. Instead of going down by 1, we go up by 1. Instead of multiplying by this, we multiply by the reciprocal, right? So this antiderivative is going to be 2 times x to the 1/2. I'm going to go up in power, which is 1/2, right? -1/2 plus 1 is 1/2. And the reciprocal of 1/2 is 2. So this is going to turn into 16 times x to the 1/2 power plus c. 1/2 power we can rewrite as square root of x, or you can keep it as 1/2, but this is its antiderivative.